guess my first question is, I saw your rocket is 210 inches long. It's very impressive, but you want to discuss some of the pros and cons of making such a long, skinny rocket?
Shirley, do you want to take that, actually?
Yeah, sure. So yes, the rocket is long. It's not intentionally that way. It just ended up turning out this long due to just all the stack up of our avionics and our long oxidizer tank. But some pros for stability: the longer the rocket gets, the more stable the rocket is. But structurally, the longer the rocket, the more chances there are of like aeroelastic effects. So with shorter rockets, you tend to not have to worry about like the rocket bending in flight due to the aerodynamic loads and stressing it in ways that are unpredictable. So yeah, with longer rocket, it becomes really critical during like manufacturing and assembly to make sure that all the sections of the rocket are really aligned axially.
How would weight and drag be different if you had a shorter, fatter rocket?
Well, it would impact the weight and drag in a positive way. So the shorter the rocket, like the less drag area and the less mass, and a fatter rocket also has less area relative to a thinner rocket of the same volume.
You're going subsonic, is that right?
So we are like really in the sort of transonic range according to our simulations, but we do expect to be subsonic to transonic. We don't expect to be anywhere like above Mach 1.
Okay. Yeah. At subsonic speeds, the total skin surface area is very important. But when you start getting into transonic speeds, the cross-sectional frontal area starts becoming more important.
Okay.
Because of the shock waves.
Oh, so that would probably be because the shock waves essentially become the skin of the rocket effectively and form like a aerodynamic body that's a bit different from the actual body shape of the rocket.
Okay, so going on to another topic, I noticed you've got plans for composite body sections, but you did a test flight with metal body sections. Am I remembering that correctly?
No, we haven't actually had any test flights. Previous rockets have used composite body sections, and even before then, we did have metal as our body structure as a result of us just using our oxidizer tank as the body of the rocket.
Okay, so I guess I didn't get that from the video, or I missed that in the paper. I guess I was just going to ask kind of about the trade-offs. Well, I mean, I can still ask, what are the trade-offs between metal or composite airframes?
Yeah, actually, Shirley's our co-team lead as well as our airframe lead, so I think she's best to answer that.
Sorry, forgot to unmute. Yeah, so some of the advantages of composite materials and disadvantages that we're aware of, there are a lot more concerns in terms of disadvantages about bolting assemblies to the airframe. So it's very important for the fibers to be continuous, and that means not putting holes wherever you want, which can make design for manufacture a bit more complex. So we tend to, in our assemblies, we tend to focus on joining and bolting to our metal bulkheads. So we have lots of hard points on our bulkheads. Our launch lugs attached to our top and bottom bulkhead on our oxidizer tank, and our plumbing attaches to the top bulkhead. Our injector and fill plumbing attaches to the bottom bulkhead. So we do have to be aware that if we are attaching things to body tubes, we will generally use adhesive.
Okay.
We do have two holes in the upper section. We do plan on having 2 holes in the upper section of our rocket for flight footage, but we are going to do a 3-point bend test with the exact same configuration that we would have in flight to validate that having those 2 holes for our flight cameras will not reduce the strength to an extent that it would cause an in-flight failure.
Great, great. So you're using a reefed chute for your fast descent phase. How did you go about calculating the descent rate when you're under the reefed chute?
Yeah, most of our calculations are taken from NAC's recovery manual, but we have our recovery lead here, Chris Sankey, so I can let him elaborate on that.
Great.
Yeah, so most of the calculations were done based on experimental data. So we've been conducting truck tests in both the reefed and unreefed state. What's really handy is that we're using our existing main parachute to reef, so we know how fast then the CD of that data. When we did, obviously, since we've used it over the years and had more tests with it, we're hoping that we'd also get some better data to reduce the noise that we get from the truck because of wake effect, getting into our university's large-scale wind tunnel. But due to COVID, we've had a couple of issues with that.
Great. That's great. All right. So now I'm going to get to the really cool part of your rocket, the Inconel 3D printed nozzle. How did you calculate for the water cooling? How did you calculate, that it would be enough to keep the thing from melting? How did you calculate how much water you needed for a full duration burn? How do you keep the wall from running dry? All those questions.
Yeah, so I can take that one. Certainly there's a lot there. We just gave a 20-minute presentation on the whole thing. In terms of our general approach, we really relied heavily on ANSYS for those initial heat transfer simulations to see how heat actually flowed through the Inconel nozzle itself. Most of those heat transfer numbers originally come from a model of our engine and rocket propulsion analysis, the software tool. So we took those heat transfer coefficients, put it into ANSYS to look at the temperatures we're looking at. And then we also have a decent number of hand calculations where we look at the total heat flow through various sections of the nozzle, compare that to the enthalpy of vaporization for water. We factor in things such as the energy required to heat up the water, as well as the nozzle itself. In terms of running dry, we certainly put a fair bit of time into optimizing our geometry. So we have a thick enough jacket of water for most of the length, and then a larger reservoir near the top. So that keeps most of the water well cooled. And then as that boils away, we've looked at the heat loads and we've simulated this in ANSYS and seen that that initial converging section, the heat loads are lower compared to something like the throat, where the heat loads are very high. So we can get away with losing cooling at the very top of the nozzle. So we've certainly done a lot of ANSYS simulations there to work it all out.
Nice. If you were to switch your nozzle to be a regeneratively cooled configuration, what would you need to do? Yeah,
so I mean, a really big issue there is we're a hybrid, so we have a solid fuel, that's not an option. And then we have nitrous oxide as our oxidizer. Honestly, we wouldn't want to try to do that with nitrous oxide. The risk of decomposition is really high. We'd be guaranteed to blow up a few nozzles just trying. So maybe if we switch to liquid oxygen, you could look at it, but overall oxidizer-based regen systems are not fun. It's especially complicated on the hybrid as well, because we have a 5-inch combustion chamber and a 6-inch rocket. So there's really no room to run those propellant lines down to the nozzle and back again. And yeah, it's overall, it doesn't look good for hybrids. We are looking at doing liquid development, and maybe in a few years, we might reconsider the regen thing when we have a liquid fuel to play with that's much stabler as a coolant.
Great. Yeah, that's a great answer. Yeah, that's all the questions I had written down. Rick, did you want to jump in with anything?
See, I don't, let me look down here real quick. Hold on. something. I asked most of my questions when they gave their presentation. So how many folks you expect back next year for seniors and juniors? Any feel for that?
You mean back to like Spaceport Record Cup, or just in our team in general?
Or just gonna, how many people, starting in the fall, the team's going to get back together? How many how many juniors and seniors you expect to have there?
Oh yeah, so we expect probably to have about 15 to 20 of our like experienced members there in person, but we will have also a few that won't be able to be in person because they'll be on work terms or co-ops or working or just studying remotely. We do attract a large crowd of first years as well. So we do expect to have a lot of recruitment opportunities as well in the fall. I think last time we were able to do an in-person fall recruitment event, like our first kind of outreach meeting, we had something like 50, 60 interested people join, of which I think probably about 10 or 15 actually stuck around and are now our more experienced members. Some of them are here today.
So your Waterloo allows all the school clubs to have recruitment events in, and you bring the rocket out, I take it?
Yeah. So I mean, in more normal times, we'd have big like all the teams would come out, and there would be a big day when recruits are able to come out and talk to the different teams. We're able to show off our hardware. We haven't quite heard how it's going to work yet in the fall. It may be a virtual event, but they're also like, we're going to be kind of transitioning back to in-person work. So hopefully we'll be able to do some in-person activities as well.
Yeah, we really enjoy getting to give those outreach presentations and get to talk to people about rockets.
Nice.
Good. We like to see that. I want to ask Ms. Kong, that's the hardware you guys won in the last few years, isn't it, behind you?
Oh yeah, it's actually just on the top shelf of our hardware shelf.
Okay.
I just kind of plopped my laptop down and yeah,
that looks very nice. You guys are well organized. Let me tell you, you'll do well in the future. You'll do well in the future.
That means a lot to us. Thank you.
Thank you.
Logan, I see Mr. Herrera, you're here. Any more questions? Follow on?
I'm happy to repeat what I asked in the earlier presentation, if that would be helpful.
Sure. We got 2 minutes.
Oh, well, I think 2 minutes are challenging. I'm going to defer then.
Okay. I don't have anything since I heard your presentation. It looked real good. No, that's it. Bob, Logan, you guys can blast out. We've got the team from Poland coming after you guys. So good luck, and we'll hope to see you next year when it's for real, or when it's actually in the desert. All right. All right.
Yeah,
good luck.
Thank you so much.
Have a good year.
Looking forward to it. Thank you. Take care.
Oh, thank you.